Thank you for being here. I noticed I was scheduled at the same time as the Python for Evil talk, so I'm glad that you're interested in using your powers for good. Um, so I'm going to talk today about making MIDI music with Python, and we're going to start with talking a little bit about music theory and how to represent notes and rhythms at first as strings and then as Python objects, and then how to generate MIDI files of the results. And so by the end, you'll be making music with Python. A little bit about me first. I have a bachelor's degree in music education from Portland State, where I was a huge choir nerd. I've been a chorister all my life, but then I went and studied full stack web development at PyDX Code Guild, and I like Python, Django, JavaScript, open source stuff, and the pop hits of the 15th century. Not a joke. And I'll play an example of one of the first things that I coded up with Python here. Bear with me. So this is a MIDI rendering of a Renaissance vocal piece from 400 or 500 years ago. So just a little sampling of Renaissance music. And I think it's amazing that there's 500 years of music history between when that was written and what you heard just now. And so we're going to take a look over the course of this presentation about how that happened, and at the end I'll play it again and show you what the code looks like. So to do these things, you'll need a way to play MIDI files. Some media players automatically support MIDI files, some don't. I had to find a plugin to support MIDI files on mine. We're going to use a library called PyCnon, which is available, or my fork of it is available on GitHub. And the extra goodies is some extra examples with the Python files and the generated MIDI files and the slides for this presentation. So, right into music theory. Essentially, music maps two things: pitch vertically and time or rhythm horizontally. And my goal here is not to dump a bunch of traditional music notation on you, but to just talk about the underlying musical structures that we can bring into code, bring into Python. So starting with rhythm. Rhythm is organized around this idea of the beat, and we organize those beats into repeated cycles called measures or bars. And so we count these with numbers, and so if you have 4 beats in the measure, you count to 4 and you start over. This is prevalent throughout music history. This is the most common meter, so common that it's abbreviated with a C for common time or common meter. And you can hear that in music everywhere up to the modern day. The drummer counts 1, 2, 3, 4, and then it starts. So, but really, measures can have any number of beats, and you just declare it at the beginning, and you can organize the rhythm, organize the beats in how whatever way works. And we'll see later that PyCnon doesn't actually. I'm going to carefully pronounce PyCnon because it sounds a little bit like Python, but. So PyCnon doesn't care what the meter is, but a lot of music composition software does care, and it's an important part of how rhythm is organized. So I thought it was worth mentioning. So taking a look at the measure of 4 beats again, these are quarter notes, which unsurprisingly take up 1/4 of a 4-beat measure. And luckily for us, this is easy to represent in terms of fractions or floating point numbers. Those are easy to bring into code. We can represent rhythmic values of different lengths by multiplying the length of a note by 2 to get notes longer than 1 beat, or dividing by 2 to get notes shorter than 1 beat. So here you see the traditional notation on the left and the fractions on the right. Another way to look at this is as a tree where the total of all the notes on each level adds up to 4 beats. The method of dividing the length by 2 doesn't account for all rhythms, and more complex rhythms can be made by combining and augmenting these, but this is enough to get us started. But we're going to use integers because if we go back to the previous slide, the numerator of the fraction is always 1, so we can use integers with no loss of information. And this is, I went backwards. Okay. Integers. So as the numbers get bigger, the notes get shorter. And this is a way that a lot of music composition software represents rhythm. So those are notes. What about silence? Silence in music is called a rest. Here you see 2 quarter notes followed by a quarter rest, and a whole note followed by a whole rest. We're just going to use the letter R to represent a rest, which simplifies our lives somewhat. So here's an example of what it looks like in code. This is not exactly Python code, but it's pretty close. My example class is a rhythm sequence where we're just representing rhythm with no pitch yet. So here, the first line, we have 4 quarter notes, then we add in some eighth notes, and the bottom line here shows some rests. And a new feature that was just added to Python is this idea of dotted rhythms, which allows you to get some more gradual increments of rhythm. So that what the dot does is it adds half of the original value of the note. It gives the note 50% more length, so you can get some of the more in between lengths, and that gives you more possibilities. And we'll see what that looks like in code at the end. So here's an example of what that might look like. Sooner than I thought. So this is an example that you might not recognize by looking at it, but I'm sure you all know this tune. Bum 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 bum. That's what it looks like, both in traditional notation and how you might write it in Python. And we'll talk about some of the details of that soon. So that's basically the idea of rhythm. You have the beat, and then you have ways to get notes that are shorter than 1 beat or longer than 1 beat, and augmenting it with the dot. On to pitch now. If you've ever looked at the keyboard of a piano, you've seen one example of how notes are organized. The distance between each note or each key is called a half step. Those are some half steps. And here are some whole steps, which is a combination of 2 half steps, unsurprisingly. Each note has a letter name from A through G. After you get to after G, you start back at A. A, B, C, D, E, F, G, and then A again. And lucky for us, letters are easy to represent in code. So here's another demo adding the note names in. You specify the letter name and then the rhythm, separated by spaces. And this works the same way for rests. You can see the second line of code there can include rests. And something interesting that Python does, looking at the red lines at the bottom, you can see that I'm not specifying the rhythm, but Python will apply the same rhythm to notes if you don't specify it. It'll apply the rhythm from the previous note and just keep applying that unless you change it. So you can see what the equivalent would be on the right here. And that's just a nice little shorthand. But it makes it difficult sometimes if you're trying to figure out what a note is out of context. So that only gives us the 7 white keys on the piano. How do we get the other 5 notes. We need some extra information, and these are called accidentals. It's a couple of symbols you can add in front of a note to raise or lower the pitch. The sharp, which looks like the hashtag or pound sign. I'll call it a hashtag anyway. Raises the pitch by a half step. This red arrow is pointing to an A sharp. And the flat lowers the pitch by a half step, the blue arrow. And that sort of looks like a lowercase b, so that's what we use for flats. And this gives us access to all 12 notes. Unfortunately, it means that some pitches have more than one name. And there's another naming issue, which is that if I play an A, how do you know which A to play? So we need to know one more piece of the puzzle, which is the note's octave. Notes that have the same name are an octave apart, or any number of octaves apart. Octave because they're 8 letter names apart, hence the oct prefix. Python uses a default octave of 5, which is right in the middle of the MIDI pitch range. And that's also a middle C, I believe. There are a couple of ways to designate octaves in code, and we'll look at the way Python does it. Python uses upticks and downticks to specify the octave. So you have the default octave of 5, and then you can add commas to go down any number of octaves or apostrophes to go up. The one peculiarity with this is that both no ticks and one uptick are both the default octave of 5, and we'll take a look at why that is right now. It's so that you can get back to the default octave in some other way than just not putting a tick, because if you don't put anything, Python just applies whatever came before. So you need another way to say, bring me back to octave 5. So here we see, in the first example, they're all C's, but they're actually distinct notes. They're actually distinct notes. The first one's an octave 5 because there's no ticks, and then we go down an octave, and then Python applies the same one, and then we go back to octave 5 using one tick, and then we go up another octave. And I'm doing the same thing in the next example, including some accidentals and including starting in octave 6. The one peculiarity with this is that you would think you start in octave 5, then you add one tick and you go up an octave, but you have to actually add 2 ticks to get up 1 octave at the beginning. Just a little bit about what's in Python. You have a class rest, which has a duration, and that's basically it, because it doesn't need any more qualities, and you can stretch that or change the duration at your leisure. The note class has all the things that we've talked about. The note names, this is the value property, that's the note name converted to an integer. It has the octave, the MIDI number, the duration, the volume, and verbose string representation. And all of this information is actually available. The author of Python, Pedro Kroger, has a book called Music for Geeks and Nerds, which I borrowed from heavily for this presentation, but he offers the chapter on how to use Python for free on his GitHub repo. So you can go find all of this information. Other methods, you can transpose, you can invert, you can do some interesting transformations, and I won't bore you with all of this. But the note sequence, which is what we've seen demos of mostly, is a list-like object. It supports a lot of operations that you'd find on lists, as well as adding and multiplying with the built-in operators. And you can instantiate it with the string or list of objects or read from a file. And again, it has lots of methods. I won't bore you with all of them, but you can invert and flip and play backwards and look at the music from all different angles, move it up and down, and transform it in interesting ways. But on to the meat of generating MIDI files. This is how easy Python makes it. There are 3 basic steps. You have your notes. Step 1, get some notes. Here you have 2 note sequences. They're actually the same notes written 2 different ways. And now you can appreciate how brief and wonderful the string notation is compared to creating note objects with pitch and duration. And again, you specify the pitch when you're creating a note object, you specify the pitch with an integer and the duration as a floating point number, or in Python 3, because you have float division, you can use a fraction as well, but if you're in Python 2, you need to import real division. So step 1, get some notes. Step 2, create a MIDI object. Here we have a MIDI object with 2 tracks, so we have 2 lines of music that are going to be played on top of each other. And then you sequence the notes into their own tracks, in this case. And then you write the file. Pretty simple. Just some things that aren't shown here. The MIDI object has an instrument property. There are actually 128 and actually more than that different MIDI instruments you can play with. You heard an example of some of the string sounds at the beginning, and I'll play that again. The default is the MIDI piano, which is 0. You can search MIDI instrument codes for details. And I found that the support varies a little bit from MIDI player to MIDI player. I couldn't get all the instrument sounds on the first attempt I made with the timidity on the command line. MIDI also has a sequence chords option, so you can play block chords that this note sequence will get played all of those notes at the same time. And then the sequence notes has a time parameter, which is a badly named parameter. It should have been called delay or rest, because it's the number of beats before the note sequence starts, which gives you all sorts of interesting possibilities for independent lines of music and staggered entrances, and I will actually give a demo of that soon. You probably all know the tune Frere Jacques, Frere Jacques, Frere Jacques, I don't know the French words, but you all know the tune. And I'll play an example of what you can do, what I did in Python with this. Here I just broke up the notes into 2 different sequences so it fit on the screen. But you can see I'm putting all the notes back together. I have a MIDI object for the 2 tracks again. And then I'm putting the same notes into 2 different tracks, and I delay one by 8 beats. And that gives us a round, and I'll play that for you here. Okay, so you'll hear the first part come in, and then 8 beats later. Oops, if my sound will work. Input error. Uh-oh. Bear with me. That might work a little better. So that's just a little sample of what you can do with that. And you heard the MIDI piano default instrument there. But lots of exciting possibilities. So that's basically all I have. I have a couple more demos. I could show you the first thing that I ever created with Python. And it's some more very old or very new music, depending on how you look at it. So the very first thing that I coded up with Python. Yep. So that was it. That was my hello world with Python was that. I'll just make a couple of notes before I end here. The toughest thing that I've found is dealing with that octave notation and getting the octaves right. Even if you put a melody together and you have all the right notes, it can be a little bit jarring and hard to tell by looking at the code what octave you're actually in because it depends on the context. So I'll just play an example of one of my early efforts at creating a more complex melody. Yeah. Yeah, so part of that difficulty comes from writing in anything other than the key of C, because the octaves wrap at C. So if you try to go outside of that without changing the octave, you just get the note that's in the same octave. So that's even for somebody like me who's pretty experienced, it was difficult to adapt to that new way of thinking about octaves. But yeah, that's basically all that I have. So these are some resources that I used, some that I used in the talk. Pedro Kroger's book, Music for Geeks and Nerds. The chapter on Python available for free on GitHub. The Complete Idiot's Guide to Music Theory, which is not free, but still a good book. Teoria.com is an excellent free resource for learning music theory and reading music, and it goes over in more detail the actual notation and music theory concepts. Also good, musictheory.net. And the Python Music Wiki is where I discovered Python. It's a list of all of the different kinds of software, music related, that use Python, from media players and audio file manipulation and composition software and all sorts of interesting things. So highly recommend that as well. Again, the slides and everything are on GitHub, and I guess we have time for questions now. Thank you very much. So the question was about the music XML format and capturing some of the subtleties that maybe this kind of notation couldn't capture. And that's true. This is not designed for capturing those subtleties. This is a more of a teaching library and for talking about and exploring some of the more basic concepts. We're not even talking about intervals or scales or any of the more organized parts of music theory. We're just putting notes into a list and arbitrarily playing them, and this Python library is not equipped to handle those subtleties. So there is another format called ABC notation, which is similar to the string format that we've used, that does try to capture some of that with the octaves and clefs and rhythm. I'm not an expert on any of those formats though, so I've used Music XML to export from other composition software to go from, like, so Sibelius and Finale are two of the big notation softwares, and I've used going back and forth between those as a format for that. But I know nothing about the Music XML format. I'm sorry. That puts it into what? Into I'm not sure about that. I'm not I haven't dealt with music XML much. I don't know. Does anybody else have an idea about the notation formats and? Yeah. Back there and then well, PyCon doesn't offer that as a an option. The difficulty with reading MIDI files is it can be done, but MIDI doesn't store audio information in the same way that other formats do, like an MP3. It's based more on trigger information, note on, note off, in this channel with this length and things like that. So there are libraries and other composition software that can do that. The big ones, Finale, Sibelius. I don't know if MuseScore will read MIDI files or not, but yeah, there are programs that support that, and that will even take a MIDI file and try to reverse engineer it and turn it into notation. Again, that's difficult with the way that MIDI separates channels and tracks and everything, but there are some efforts that do well with certain things in that way. I haven't done that. Yeah, so the question was, have you ever tried to create a random string of notes? And the answer is that I haven't done that. In Pedro Kroger's book, he uses that as an example, though. You can just create random or use any number of mathematical functions or yeah, you can go wild with the algorithmic music composition and then create some pretty interesting things. I don't know if you'd want to actually listen to most of it for very long, but yeah, you can certainly. There's lots of possibilities there. Sure. Yeah, you could say for X in this note sequence, do create another note sequence. And actually, there's a function called Harmonize, which you can use on a note sequence or a note object that will actually just give you all of the harmonizations of every note in that sequence. So you'll just get a bunch of notes back from that based on the notes that you put in. And again, there are all those transformation functions, inversion, rotation, that you can use as well to sort of explore the different aspects of your notes. Yeah. Okay. Anything else? I'm happy to help people get set up with PyCon or answer any music-related questions. You can get in touch with me anytime. I do when it depends what my goals are. With this, I'm just doing it for fun. It's hard to be efficient when you're writing in the string notation. It's much easier if you're trying to get something done quickly that you use a GUI and have the staff and notes in front of you and click and drag or play from a MIDI keyboard or something like that. Unless you type very efficiently and you're very comfortable with the shorthand. I like Lily Pond is one that I've used that uses a notation similar to the string format, and that's good as well. But that has kind of a steep learning curve if you're not not prepared for it if you're used to a GUI. But I think the GUI programs like MuseScore is a good open source one. Yeah, I haven't used that one.
Like I say, if you're just getting started and are not familiar with notations, probably something like MuseScore is about as easy as you can find to
Yeah.
get started. Provides really nice interfaces and stuff. Willipon definitely produces the nicest typeset music. You know, it's traditional notation with anything out there, and that's what it's for. And so, yeah, those are your sort of two main things. Notations like ABC notation are nice and probably a little nicer.
Mm-hmm. Yeah, and I think more of the point of PyCon is to sort of abstract you away from the traditional notation and just teach music theory concepts. But if you want to get into more of the notation, any of the GUI programs like MuseScore or even LilyPond, if you want to jump into that, that's a whole language for typesetting sheet music and written scores. So we have a couple of minutes before lunch if anybody has any other questions. Otherwise, we can go to lunch early. Resounding. Let's go to lunch.